Thank you to everyone for coming. Thank you for letting me into your living rooms. So yeah, what I want to talk about is something that I often kind of hint at. If you've seen me talk about Idris before, what I've generally done is I've talked about, I've given an introduction to the language, I've given a whistle-stop tour of what it can do. And there's a bit at the beginning where I like to show one of the values of types is that not only can we use types for all the standard stuff that we say are benefits of static types of correctness and efficiency and writing safe generic programs and safe refactoring. One of the really interesting things for me about types is the way they help you as a kind of design tool. They help you build the program and they help you use the machine as your friend rather than your kind of your adversary that you submit the programs to and the computer shouts at you that you got it wrong. So what I want to do in this talk is talk about the type-driven interactive editing side of programming in Idris. And particularly, I want to talk about how Idris can use the type to generate programs automatically. So I'm going to start with just showing you several examples of what it can do, because it's good if you know what the limitations of the system are. So not only the strengths, but also the limitations. Obviously, I'm steadily trying to remove the limitations as time goes on. But if you know what it can do, and if you know how it works, then you can always use the tool more effectively if you know things to that level of detail. So I remember a thing that my advisor always used to say to me when I was struggling with using a new tool and kind of getting all sorts of error messages. He would implore me to be the machine. So if you can understand being the machine, then you can use the machine more effectively. So yeah, I'll start with showing what it can do. I'll say a little bit on the way about why it's useful. So as you may know, there's lots of work out there on type-driven program synthesis in all sorts of systems. So Haskell in particular, there's a lot of work at the minute on liquid type-based programs. So I'll mention some of the related work later on. So, there's lots of these systems available, and they all have, I think, slightly different goals. So your goal of program synthesis, it might be, I'm going to write the type and I want to generate the entire program, and I don't want to have to think about that program because the type is precise enough. Or your goal might be, so this is the Idris view, your goal might be that this is a two-way process. We're interacting with the machine. Program synthesis gives us small steps. It kind of frees us from some of the more boring steps of programming, the things that you know how to do and you know how to get it on paper, and you just want the machine to put it down so you don't have to put it down on the editor so you don't have to think about it. So we'll talk about why that sort of approach is useful. I'll try to get across why that's useful. And then in the last maybe 10 minutes or so of the talk, I'll give you an overview of how it works. Now, the reason I want to do that is one criticism I sometimes see of this approach to programming with the interactive editing is, it's just a magic trick. It's a conjuring trick. And what I want you to understand is that, yes, that's right. It is just a conjuring trick. It's surprisingly simple. I think it's beautifully simple. The fact that a type system, putting a bit more stuff in the type system, can give you so much more help with only a relatively simple algorithm. And it is an algorithm. I'm using the word algorithm in the sense that it has been used for centuries, but it's not really used anymore. So it's an algorithm that a human can explain and a human can reproduce. So we do understand what it's doing. Okay, so I'll go through a few examples. And yeah, as Bob said in the introduction, please don't forget to ask questions in the chat. Usually what I like to do at this sort of event is that I can see all of the audience and I can sort of see when people are frowning or nodding. It's kind of hard to reproduce that in this sort of environment. But if you type your questions into the chat, I'll leave a few opportunities for pauses, or maybe I'll get carried away and I'm quite happy to be interrupted if I'm obviously getting carried away. Okay, so let's start with a few examples. And for these examples, I want to, as we're going, I want to show you a little bit about programming in Idris along the way. So I'm not going to teach you Idris here. I'm going to assume a little bit of knowledge. So if you've done some Haskell programming or some programming in a typed functional language with pattern matching, then this should be pretty much familiar to you. Like bits of the syntax might be slightly unusual, but generally it should be familiar. So I talk about type-driven development. So type-driven development, we give the type first, and then we interactively work towards a program. I'm just going to use polymorphic types for the moment. I'm not actually going to do many dependently typed examples. I want to show how this sort of approach to programming can work in languages that don't have fully first-class types. So, and you know, I wish I had these capabilities in an editor for Haskell, for example, that particularly these capabilities in an editor that I can give to a class of 80 or 90 students and have it work smoothly. So, you know, maybe one day. So we'll start by just writing a program that takes a NAF, so a natural number, so 0 upwards, a thing, and returns a list of the thing. So you can probably guess from the name that the intention is we're going to repeat that thing, that the generic thing, that number of times. So what we do in Idris is start with the type. We ask the machine, in fact, I could use the menu here. This is I'm using Vim here because it's a hacked Idris Vim mode that I haven't actually pushed anywhere yet, but will be available soon. But we could look at the Idris menu and we could tell it to add a clause. So it's added a candidate clause for this. This thing on the right-hand side is a whole. A whole gives us the context that we're currently in and the thing we're trying to achieve. So if I ask for the type of the whole, it says you've got a type. The 0 means you're not allowed to, or that type is not available at runtime. We can talk about it, but it's not available at runtime. We have an X of type A, we have a K of type NAT, and we're trying to get something of type list A. So you probably know how this goes if you've done some functional programming before. We pattern match on the natural number. That's either a 0 or a successor. Again, I'm going to use the Idris menu rather than the keyboard shortcuts, just so you see it happening. So I ask for a case split on this number. Gives me 2 possibilities. Again, I can check the type of the whole. I'm looking for a list. One thing I can do, which is kind of neat, is I can say proof search. So it says proof search in the menu. It's probably better to say expression search. Curry-Howard isomorphism fans will know that these are kind of the same thing. But you know, from a programming point of view, it's really about expression search. So it searches for something of type list A. The first thing it finds is the empty list. It says, yeah, that's probably okay. We'll come back to that. We're going to be doing a lot more of what does it mean for the machine to say, yeah, that's probably the thing you were looking for. And the other case, I'm going to do this by hand. This is X, and then we'll repeat K copies of X. And I can hit reload and check that it type checks. Great. So that was an interactive process of adding a definition, doing a case split, asking the machine to do the case split. In one case, I did a search. In the other case, I typed it in by hand. Now, that's actually, those steps that I'm following are steps that I follow an awful lot, and you follow an awful lot when you're writing a program. And we like abstraction. We don't like repetition. We don't like doing the same thing twice. So so Idris provides a generate definition mechanism, which, as it were, abstracts over the process of programming. Essentially, I've implemented a mini-me that takes this approach to adding a definition and case splitting and so on. And if I ask for generate definition for rep, then what it generates is the thing I just said. Because really, if you give that type, you can kind of figure out that probably what you wanted is, you know, you've got a natural number and you've got a thing. The natural thing to do, and I'll come to the definition of what it means to be the natural thing to do, because it's kind of weird, you know, what it means to be that later on. The natural thing to do is to repeat the thing that number of times. Now, when I ask for generate definition, it's not always the case that the first thing I get is the thing I want. So I sort of liken this to repeatedly hitting it with a hammer. So we could repeatedly hit this thing with a hammer and it will generate more definitions of the right type until we get the one we want. I don't have this in the menu yet, but there is a shortcut. So if I just keep pressing the dot button here, it will keep generating more type correct definitions. I think we can all agree that these are type correct definitions. Some of them less obviously useful than others. So yeah, there you go. But that's an interesting one there. But the first thing it comes up with, if I just hit generate, the first thing it comes up with is the one that we wanted. Also works for append. I've got an example here of append. So again, append, it does a case split. It does a search for the right hand side after the case split. And just the spoiler, I'll tell you what the heuristic is here. So it's generating, it's doing a search for type correct definitions, and the heuristic it's using is try to use all the variables. That's basically it. So it will generate a batch of definitions, and it picks a round number. So it picks 16. It does 16 definitions, and then it picks the best one according to that heuristic of use the most variables. Okay, so that's the general idea. That's how we do Idris programming. Now I'd like to just run through a few things that work nicely, maybe some things that work less nicely. Then I'll talk about how it works. So one situation where where I find it kind of useful is just your basic plumbing. So when you're writing a functional program, you often have a case where you've got something in one form, you want it in another form. There's a pretty direct mapping from one form to the other form. So particularly if you're taking advantage of parametricity, so there is only this uncurry function, there's only really one thing this could do, and that's to deconstruct the pair of A and B, apply this function to the pair of A and B, and then return the C that comes out of that function. So we should expect it to find that. So it does. I don't actually like that definition myself. I like to do pattern matching on the left-hand side for this definition. So I'm just going to ask it again. Okay, so I prefer that one. Curry is the same, but the other way around. So again, it's taking a couple of things, pairing them up and calling the function. I'm okay with that definition. And then this last one, this is a little bit contrived. This is, we've got a nested pair, and we're trying to extract two elements of that pair. So again, we could generate that definition, and it will happily project out the elements from the pairs. Again, I would rather do that by pattern matching. So I'll ask it again. It will do it by pattern matching. We do run into a bit of a awkward situation here, because I'd like to go a bit deeper here. I'd like to pattern match on X and Y again. And then it actually gives me something that's nonsense. So so the next definition is, oh, I'll make a recursive call, even though that recursive call isn't a valid recursive call. So it's not perfect yet. Well, I mean, it can't be perfect, but you can you can at least keep hitting the hammer until you get something that you're more or less satisfied with. So if you've got something that's taking advantage of parametricity, it works nicely. Let's take another one. What's mine? Oh, right. So we've got a dependently typed program here. Now, what happens a lot with dependently typed programs? So I'll just I'll walk you through the general idea here. I won't go into too much depth, but this is essentially a heterogeneous list. So it's a list where every element of the list could be a different type. So we need to have some way of saying what the types at each position in the list can be. So one possible use for this, so the way I've seen this sort of thing used is for extensible records. So where you could define a type just with your type level list that says what the different field types of your list are, and then you just write it out as a list. So it might be something that you can use to encode JSON data, for example. So you've got your schema, and then you've got your JSON data, and you can use that HList. The type of your HList is the schema, and then you read it in. So LMAT is, if we're going to project something out of this, we need a way of saying what the type is that we're projecting out. So LMAT is a predicate that says at position N, we have something of this type in this list of indices. So the element at the 0th position in this list has type T if the list is of the form T cons T's. And if projecting the kth element out gives us a type T in the list T's, then projecting the k plus 1th, so the next element out in a list that's one bigger will also give us a T. Now, we have already written the lookup function there. We're pretty much there. We've explained what it means to look something up. So we shouldn't have to do it again. Now, a lot of the time when you're writing dependently typed programs, You spend a bit of time up front coming up with the explanation of what it means to be the right program, and then you have to write the program again, which is the right program. That makes me sad when I have to do that. So it's nice that I've essentially written the program, so I can generate a lookup function, and there we have it. So that all it's doing in this search is it's looking at the form of LMAT, it's looking at the form of H list, and it says, well, there is only one way that I can project an appropriate element out of that list. Yes, I could ask it for another. I haven't tried this. I wonder what happens if I ask it for the next one. No search results. So that means there's no more results. It only found one. So there we go. Now, where does this work in practice? I've pulled out a bit of your actual Idris 2 implementation. So this is a part of the Idris 2 implementation where we try in the implementation of Idris 2, we're very careful with variable names. So getting variable naming right is hard enough in any kind of programming language, but there's a lot of manipulation going on inside Idris because there's sort of unification of two types. There's a lot of evaluation going on, so checking the two things evaluate to the same thing. There's a lot of substitution of names going on. So probably like 90% of the bugs that people found in Idris 1 were about naming. So I decided not to have those bugs in Idris 2. And how do you do that? Well, you use a type. So this predicate here, it's a way of saying one list is a sublist of another just by saying whether in the first list you're skipping an element or you're keeping an element. So that they remain in the same order, but occasionally we skip an element. And the sort of place where the Idris implementation uses this is, well, it's basically everywhere. But if you've got a scope with some names, and then you've got a smaller scope with fewer names, you still might want to have those two scopes working together, provided that you can prove that one is a subset of another. There's a couple of things that you often have to do with this sort of proof, which is a little bit boring, but necessary. It's things like, if you know that X's is a sublist of Y's, then you also know that there's still sublists if you add the same set of elements onto the front. And you also know that they're the same sublist if you add the same elements onto the end. Now, when I was writing Idris 2, I didn't have this proof search mechanism, so I had to implement these by hand. And yesterday I thought, I wonder what would happen. What would have happened if I'd had this in advance? So I just tried it out. And to my astonishment, that happened, which is modulo name choices. That is exactly what the implementation is in Idris 2. The next one is a little bit more entertaining. So again, I can generate this definition, and it generates me something that is type correct, but horrible. So as a rule of thumb, like none of this program synthesis really frees you from knowing what the program is doing. So it's a good idea to look at these and check that it's doing the right thing. Like in subextend, I can see that, well, I'm adding a list of things on the front. So obviously I'm just going to say, I shouldn't use the word obviously, but I did, sorry. So, I'm going to keep adding a new element onto the front of the list. I'm going to keep all of these things that I'm adding. Subinclude, I can't look at this and check whether it's the right thing. So what I'm going to do is hit it with a hammer and see if I get a better definition. And I do, so that's nice. So basically what it's saying here is that if X is a subset of Y's, I'm just going to keep going through that list. Eventually I'll get to the end, and we hit a slightly bigger list that happens to be equal. So that's nice. This is a thing that comes up in practice all the time when you're using this kind of predicate in programming. So it's nice to know that you don't have to do that boring work. Let's see. Do I have time? Yes, I have time to do another one. Let's do run length encoding. So this is another case of this is a thing that can come up in dependently typed programming quite a bit, where you have an optimized data structure and your original data structure. And you want to preserve the relationship between those two data structures. So run length encoding is the simplest example I could come up with this sort of idea. So we've got this representation of a run length encoded list. So it's either empty, which is the run length encoded list of the empty thing. We've got, or we have n copies of some element x. I should maybe say successor event there, but so this is sound but not complete. So this isn't guaranteed to give you the best run length encoding, but it is guaranteed to give you a sound run length encoding. So this will be a representation of n x's and then more of the list. And it just occurs to me that I haven't given any opportunity for anyone to ask a question. So I don't know if there are any that I should answer at this point.
We have a comment and a question from Alan Zimmerman. If you could unmute yourself and ask. Okay, here we go. Let's see.
Hi, can you hear me?
Yes, hi.
Okay, first of all, in your early remarks, you said you wished Haskell had something. There's now the Haskell language server is a tactics plugin, which I think does something similar and is kind of improving.
I would love to investigate.
Yeah, and then the second thing is how useful is this on kind of real world code? And you did just show on the Idris compiler, so there was a bit of a delay, but I mean, is it actually usable?
Oh, that delay that you saw, this is actually a little bit embarrassing. That little delay is because of the way the Idris, or the Vim mode works. So the delay is actually the Shea scheme runtime spinning up. It has to, only in the Vim mode. This is just because of the way the Vim mode works. It initializes the process. So it takes about 0.2 of a second to spin up. And then it goes. So the delay you see is a little bit artificial. So or not artificial. It's a little bit of it's not clear that delay would be a problem in practice.
What's the longest kind of delay that you've ever had to, or have you ever had to like abort?
Because if it takes more than a second, it's not going to find the answer. That's my generally what I found.
Okay.
There are a few things we could do to speed it up, but mostly when it's too slow, it's because the search space is too big, and we have not found a good way to prune that search space. But I don't tend to find that a problem, just because if it goes on a long time, you've already lost. So, but yeah, more experience is necessary. Absolutely.
Okay. Thanks.
Okay. So.
Do you have time for one more?
Yeah, sure.
Okay, I'm going to unmute John Cinnamon here, who has a question.
I think we're both hitting the button. Okay. So yeah, my question is, how much do you need to know the answer you're looking for before you can trust running the synthesis in Idris? So is it a case that if you don't know the answer, it's not worth running? Is it just like a shorthand way of saying, write this program that I already know for me? Or does it help you find novel programs that you don't necessarily know yet?
I think it's no. That's a good point for me to actually not do run length encoding and do this next example, because run length encoding is fun, but it's more of the same. It's usually better if you have a rough idea where you're going, because then you can look at the program and say, yeah, that's what I meant. But this little example here that I'm going to finish with before I do a quick summary of how it works. This is the continuation monad. So I kind of borrowed this from how Haskell does it. Essentially, this is a way of saying you have a computation, then you're going to do something with it when you finish the computation. So it is a monad. I'm not going to explain what it's all about. I'm just going to say that it is a monad that allows you to express what's going to happen next. And what we should be able to do, and I said it's all about monadic plumbing and trying to. One thing is that this is good for is helping with monadic plumbing. So, and one way of understanding a bit about what this continuation monad is supposed to do is actually to say to the machine, well, I know what the type of the pure and bind operators are going to be. So I haven't put these in an interface because it's a bit fiddly. But if you show me the implementation, I might get a better understanding of what's going on. So I'll generate the implementation of pure for it. And it says, okay, if we're returning a value, what actually happens is we return the value with the continuation applied to it. And then we can say, well, how does the bind operator work? Well, I'm just going to generate the bind operator. So I'm not going to go through this. I'm just going to promise you that that's correct. That the way I would, I mean, to be honest, I don't fully understand continuations. If I try to explain continuations, it will just show up the fact that I don't properly understand continuations. But I know that this is a correct implementation because I looked it up. It is following the sort of pattern that I would do if I was writing this program. I would say, you know, let's just look at the types to see what even works. And just to kind of show that also works in a more sort of more expressive setting, you know, if we've got the monad transformer version of this, this may be the first time I've said the phrase monad transformer in a conference talk for a very long time, but the monad transformer version of this, it's also happy to find that one. And entertainingly, this was a challenge that was given to me a couple of months ago. It was, all right, what about call with current continuation? Now, I'm definitely not going to try to explain to you what call with current continuation does, because that really will show up a lack of knowledge. But fortunately, the machine knows how to implement it. And again, the only reason I know this works is a combination of it type checks, and I looked up the Haskell implementation, which is modulo record projection is the same thing. So I was really pleased when that worked. I was quite surprised, but yeah, it comes out okay. So this is an example of, these are 3 examples of programs that I have no intention of ever writing. And I'm really glad that the machine can write the programs for me. Now, I might be a little bit worried if I didn't have a Haskell sort of Oracle reference to look at to check that they're okay. So I would probably have to resort to testing. You know, I do test my programs. I like to, you know, type-driven development doesn't free you from testing your programs. You still have to see that they do the right thing. Okay, so that's a variety of examples that it can do, and I think it's important in these last, I don't know, maybe 5 minutes to do this. So it's important to understand at least a little bit about how it works, because there's really very little to it. There's pleasingly little to it. And it relies on having a little bit of machinery already available in your system. So if you have the machinery for interactive program editing, and I encourage all language implementers to do this, because it's so nice to be able to ask the machine to do some of the more boring bits of typing for you. So if you have that, you already have the mechanism to allow the system to explore possible implementations of programs. So it's essentially a type-driven search. We'll look at the whole. We'll build programs incrementally by looking for things that could possibly fit that hole, and we'll only explore the well-typed paths. Having holes is useful because we don't need to construct the entire program in one go. For example, if we have a vector of a particular length, all we need to do is say, well, this has to be a cons because the vector has something in it, and then just recursively search. So the individual steps of the search are quite simple steps. It's and we just need a mechanism. I'm using that word just again, but we need a mechanism to be able to say, what do we do if this succeeded? What do we do if this didn't succeed? So the primitive operations you need are holes. So having holes, at least as part of your internal representation, if not part of the language, you need to have unification. So this is for holes with one possible solution, but it's also for checking whether the thing that you've generated is type safe with respect to the thing you were looking for, and then case splitting in order to refine the function inputs. So this is, you know, these 3 things are the sort of the things I use to implement the virtual me that writes the program by generate and test. So a couple of, I know I don't need to, I do need to talk about them a little bit. So I'll just point out about search. So this is a bit of the Idris internal, slightly simplified. Everything happens in this kind of God monad of the Idris core. This gives you access to bits of the elaborator. Particularly, it gives you access to unification and all of the definitions. But a search result is either going to be, we've lost, there are no more, or we're done, there are no more search results. Or it's going to be an individual result, and then what we do if we're not happy with that result. So we got our first result, and then the continuation of the search. So the outline for expression search, basically fits on a page. There's a bit more code than this, obviously. You know, there's a bit of draw the rest of the owl going on here. But given trying to solve a whole of type T, we'll look at all of the local variables with a bit of refinement just to do some projection. So if one of them works, brilliant, we've won. Then we'll see, well, is it a function type? If it's a function type, we'll make it a lambda, because what else could it be? I mean, the function type might have been solved by one of the locals, but if it's a function type, it's probably going to be a function. If it's a data type, then we'll look at every constructor of that data type. We'll try them in order. We'll only try them applied to new holes. So we'll generate some new holes and then unify the thing that we've just invented with the type we're looking for. And if that doesn't work, we'll try a recursive call. So with the descending argument we saw earlier in select thing, that doesn't actually do that. It should. It's got the information, it just doesn't check properly. Always solve with a recursive call. So that's how we get expression search working. I've got a little example here. I don't have enough time for this, but this is essentially what you would do when working through a vector. Is, you know, you search for the whole thing. It must be a cons. The first thing must be an x. The second thing must be an append, or the second thing, the only thing we have left is to try the recursive call. When we try the recursive call, there's only one thing that the argument could be. So I've run through that very quickly, but it's essentially following that algorithm. And the final thing of program search is a remarkably small step. And I think I basically implemented it over a weekend. It was just, oh, I wonder if this works. Wow, it did. So program search is the composition of case splitting, which we do in the editor, and expression search, which I've just kind of very briefly outlined. So what we do, generate an initial definition, we get the number of arguments by looking at the type, and then we apply the expression search to the right-hand side. If that didn't work, so this is the search monad, if that didn't work, we pick one of these arguments to split. That gives us more clauses. We try again. We just keep doing that until we reach a depth where we think we've gone too far. So in practice, it works left to right. It doesn't split to a depth greater than 1. That appears to work pretty well. I imagine these things could be configurable. At the minute, they're not. And the final thing, the simple heuristic. So the search monad gives us a result and a continuation. The user can always say, after you've got a result, so in the API here, you can always say, you know, hit it with a hammer, give me the next one. So we don't just give the first result, because the first result is going to be like the first constructor. So for lists, the first result is going to be the empty list, for example. So we just arbitrarily pick this round number of 16 at a time. We order by the most local variables used. And I mean, the rationale for that is if you've written down an argument, you probably wanted to use it. So that seems to be a reasonable heuristic. Turns out to work pretty nicely in practice. So this was a suggestion I got from Leonard Augustin, who implemented a very similar system for Haskell. Did this in Gin and saw that it often gives you the result you want. So you don't actually need a lot of fancy trickery in the types for this to work effectively. What we really want is to have the interaction in the editor for things to work nicely. No, I'm not going to talk about that refinement because, again, it's more of the same. It's just to say that we can go a bit deeper. If we get properly stuck, just say if we get properly stuck, we can go a bit deeper. We can make an intermediate definition with a local variable. So there's loads of work. It seems to be a fairly trendy topic at the minute, actually, which is great because you know, I can look at these papers and steal their ideas. It's a lot of it is following this basic idea of only generate well-typed. Like you know, you do it incrementally. You know at each stage what the well-typed possibilities are. If you have holes and unification, it's not all that hard to do that. So Gin I've already mentioned. Agda, if you've used Agda, Agda has a similar kind of tool called Agzi, similar kind of algorithm. There's some interesting work on liquid Haskell and I've only picked 2 here. There are so many I could have picked. One particularly interesting thing we might explore is example driven as well as type driven. So not only do we give the type, but we give a couple of sample inputs and outputs and say, can you get one that also satisfies these inputs and outputs? So it might be a fun thing to explore. And then to finish, because I see I'm pretty much out of time, just as a summary. Firstly, I hope I've got across that I have enormous fun with it. I find it's really great, really pleasing to press a button and just see the program you're thinking of appear. It's just there's just something satisfying about it. It's like, oh, I did come up with a useful type. But you can always use this sort of thing more effectively if you have some idea of how it's working underneath. How it's working underneath is really just a case of case split, and then look at the possible candidates for the whole type you've got. And if you know things like, if you know what it's looking for, what kind of things it's looking for, then you might have a good idea of how effective it's likely to be in the particular situation that you're working in. A couple of things we might look at. So one thing I'm interested in with Idris is protocol correctness and communication protocols. So I don't necessarily want general purpose program search. I might want to say, okay, we're working on a protocol. Give me the next thing in this communication protocol. What is the next action that we should take? So just being able to refine it a little bit more. So making it extensible, I think, would be very useful, where the extensions can say what you can and can't do. And then something people always ask is, can machine learning help? The answer is probably yes, but I'd really like to go as far as I possibly can without doing that, because I like understanding what's going on underneath. But I bet it could help, and I bet it would be really cool to see what it could do. Anyway, I'm basically out of time. I don't know. I hope there's maybe a little bit of time for questions, because I didn't really leave enough time for you to interrupt. But otherwise, thank you for your attention, and I'd love you to have a go at this and see what you can do. Thank you.
Great. Thank you so much, Edwin. I think we've got time for one question here. Let me unmute Jim Ferrand here. Okay, Jim, if you'd like to ask your question.
Hi, Edwin. It's one of those questions I'm not quite sure how to ask, so I'll let you interpret it. So it seems quite interesting to me that certain functions are almost kind of defined by their types, whereas others are not. I wondered if there's any kind of theory been applied to classifying functions on this basis, and if we can sort of say anything interesting about those two categories, or if we're still at the place where it's just dealt with using heuristics and other sort of guesses.
Yeah, you certainly have parametricity. So where something is parametric in some of its arguments, there's only one thing the function could possibly be. So if you have a function with a suitably parametric type, then you really are saying there is only one possible implementation of this. And when it comes to dependent types, that's another way of constraining the search space, of saying, this input must be the same length as the output, or this output must be an uncompressed version of the input. I'm not aware of any theory about that, because I mean, part of it is about how you define the type. It's about learning how to define the type yourself in the appropriately usefully constraining way. And that to some extent, at least for me, has been something I've had to learn as a programmer. It would be very good if there was some kind of theory that we could explain to people about that. But at the minute, all I can really say is try it and have a go, and sort of, start with a fairly generic type, and then try to constrain the type a little bit more to see if it helps you write one function on that type, it'll probably help you write more functions on that type. That was certainly my experience with the representation of names in Idris, is that once I got that working for one thing, it turned out to help on loads of things.